All right. Well, welcome everybody. We've got another exciting day of WMS related practice and information that we're going to go through today. Before we get into that, let me just give you a couple of announcements. Wednesday we're having an exam, and I think it's going to go fine. I had an exam in a different class on Friday, and this is a group of students who aren't as advanced as you, I guess would maybe be the kind way to put it, and it went fine. Nobody had a problem. Out of 30 students in the class, I got 30 exams, and so we can do this sort of thing remotely. I'm confident. The way it's going to work is I'm going to email the exam to you at 8 o'clock. It'll also automatically be revealed on Blackboard at 8 o'clock, and you'll have up to 3 hours to take the exam. Now, I was looking through everyone's class schedule, and I noticed that many of you have seen your design at 8 o'clock on Monday, Wednesday, Friday, but my impression is that you don't actually have meetings during that time, and so you can work on the exam whenever you want between 8 and 11. Now, I know that we have from 9 to 9:50 free, and I'm going to be writing the exam so that I think the average student could finish it within 50 minutes. And so you'll have 3 hours to work on an exam that would take 50 minutes. And the extra time is just in case you have any technology related issues. And so anything that's a hand calculation, you will use Cam Scanner to turn into a PDF, and you'll upload that at the end of the exam. Anything that is Excel related, you'll upload the Excel file, and if I have a WMS related question for you, then you'd write the answer on a piece of paper, and then you'd also provide supporting screenshots as just evidence of what you had done. So it's open note, open book. You can use your previous homework assignments, and so any resource that you've got available you can use, with the exception that you have to do the exam individually. And on the cover sheet, along with the instructions, I'll ask you to sign a statement certifying that you did work on the exam by yourself without any input or assistance from another person. So are there any questions related to the test? If there are no questions now, and one pops up later, feel free to send me an email. I'll do my best to respond to that. So we won't have a class meeting on Wednesday because you'll be working on the exam. Alright, so today we are going to continue with WMS, and we're going to investigate two different models. We're going to look at the National Streamflow Statistics Model, and I kind of gave you a brief overview of that in a lecture from last week. And then we're also going to look at the TR-55 model. And so they're both relatively easy to set up, and so we're going to do that with a location that is, it's a little bit ambitious what we're going to be attempting as far as the project area. We're going to be looking at a really large watershed in the neighborhood of about 50,000 acres. It's a watershed that's south of the interstate, south of Milton. It's a rural area, and so what we want to delineate is the East Fork of the Mud River. And if you look at a map, there's actually several different rivers that are labeled on the map as the Mud River. And so let me just show you that now. Okay. All right. So here in you can see I've got Google Maps going. Let me zoom out a little bit to give you some context. And so here's Barbersville. I guess there we go. Here's Barbersville, Milton, Culloden. So south of Milton, East Mud River Road, and then there's two branches of the Mud River. They come together, and it's just called the Mud River after they join together. So there you can see the Mud River, but then there's three rivers coming together. So it's, I guess, a little bit like Pittsburgh, where there's the Allegheny, the Monongahela, and the Ohio River coming together. Well, here we've got the Mud River, the Mud River, and the Mud River. So anyways, what we're going to look at is the East Fork of the Mud River. And so this branch of the Mud River, we want to find out how big is that watershed. Oh boy, it's big. We're not going to do that trick that we've used in the past where we can kind of just rely on the shading of the street map. You know how sometimes we can kind of tell where the watershed is just by looking at, okay, well, like for instance here in the center of the screen, I can tell that right now I've got the entirety of that watershed in my view because here I've got some stream branches and they're all coming towards a central point, and then there's other streams going in other places that I know isn't in this particular watershed. So we don't have that same luxury when we're working with a watershed that's this big because, I mean, maybe if I could make the rivers bigger, it would be more obvious whether or not I have the whole branch, but the bottom line is it's going to be a little bit iterative. Like we'll try and pull up this similar project area in WMS, but we may have to zoom out and pan around a little bit before we finally have the entire watershed inside of our view. And so in my mind, for how we're going to spend our time today, a fair amount of it is just going to be getting the correct project area and just experiencing what happens when you don't have the project area and your watershed kind of artificially terminates with a vertical or a horizontal line. To give you a sense for the real world is you sometimes have to just play around with the data until you finally have your entire project area. And so I was doing this earlier this morning, and at one point I was zoomed out so far that I was getting all of our watershed as well as most of South Charleston. And so I don't think we'll have to get quite that creative, but just to give you a sense of what I think is one good way to find our watershed is look at this unusual stretch of the road where the road is going to the east and then it goes south and then it goes west again, and so it's going around some pretty big hill, that East Mud River Road. That's a very distinctive feature that remains distinctive as you zoom out and as you zoom in. And so where you don't have city names, like when you're in a really rural area and there's not an obvious city name that's going to help you identify the project, what you can look for is roadway shapes. And luckily we have a pretty distinctive roadway shape that's pointing. It's pointing at the East Fork of the Mud River. So that's what we're going to tie together as our indicator of where we're working. So any questions so far on the objective for today? Alright, so if you haven't already, go ahead and fire up WMS. I got a message over the weekend from one of the students who said that they were having some licensing issues with WMS, and I hope that that was overcome. I didn't hear back, but if anybody has an issue where it says that it's not licensing, my initial suggestion is to uninstall the program and reinstall it, or if you go here into Help, Register, you can enter in by clicking on Change Registration. Then you can just type in the serial number that I gave you the first time around in the email. But you may have to uninstall and reinstall. But let me know if you have any problems related to that, because that hasn't happened again. It hasn't happened before, so I want to be aware of any difficulties you're facing. Alright, so here we are in WMS, and probably when you begin the wizard, you're going to be prompted for whatever name you were working on most recently. And so I'm going to change the location, and maybe what you ought to do is, if you have a folder where you're saving all of these exercises just as a reference, create a subfolder for each activity on each different day. So I've got Monday the 6th as a folder, and here I'm going to call this Milton 3 because it's the third time I've looked at this watershed south of Milton. Alright, and then within that subfolder I'm going to create a WMS file and save it. And then you'll notice that it hasn't actually created the file name until I click on the Save button. And now we can see the file name in all of the window locations. Alright, so this is the tricky spot, is our project area. Now, if you don't already have the projection defined, go into Define, set a global projection, and in your list of recent projections, select one of the Zone 17 projections, whether it's WGS or NAD. Not a latitude, longitude, but one of the Zone 17 projections. Alright, make sure that your vertical datum is set to meters units, and you can use, I think using the most recent vertical datum probably makes good sense, and so set it to meters and OK. Now, defining the boundary, this is where we're probably going to have to go through a couple of different iterations, and so just looking for our project area, let's pan and zoom a little bit. So we have Milton and Culloden. If we go back to this view of the street we were looking at earlier, let me just pull that over separately. Alright. So it's right on the border of Milton, Culloden. There's this road that goes south, and then here's that distinctive feature that's pointing the way towards our watershed. So let's see if we can identify that same kind of view in the project boundaries. Alright, so we're going down south with this road, and then here it is, that target that's pointing towards our watershed. So let's drag it like this because it's the East Fork, and so it's all to the east of this junction. But the question is, how far do we need to zoom in? Now, this street view is a slightly different shading of the street view that we saw in Google, and it's maybe a little bit more obvious where some of the watershed boundaries are, but still, it's going to be tough to know if we get it all. So we'll just start with the view that looks approximately like this. So we've got our pointer on the left side. You can see Turkey Creek Road on the right, and I'm going to click OK. Now yours is going to be slightly different from mine. That's alright, but let's just go ahead and get only the elevation data. Don't bother with the street image or the topo map or anything like that. Just get the elevation data, and you click download data from web, and now it's recommending a resolution based on not wanting to spend too much time downloading the data file, and then if it's too high resolution, it's going to take a long time on Topaz to calculate. So just go with the default for now. 30-meter resolution is plenty. It's each elevation cell has a width and a height of 30 meters, and that'll be good for us. So click OK, and it loads it there in the background. We can skip right ahead and have it calculate Topaz. Alright, close that, close this, and then let's take a look at what we've got. So I'm going to turn off the elevation heat map, and I really just want to look at Topaz. And so I can see that East Fork on the screen. In fact, I kind of don't even need the street mapping, because if I zoom in, this is where the East Fork is meeting with that South Fork of the Mud River. So it's the Mud River, and the Mud River all coming together. But if I zoom out and try and ask myself, do I think I've got all the elevation data? Like, is the entire project, is the entire watershed boundary in here? It's not looking good. Like, anytime the river just kind of stops, that means that probably there was more river on the other side of our watershed, over on the east, that I didn't get. But let's drop an outlet and have it delineate anyway, and that'll maybe give me a sense of how much further out I need to zoom and what direction I should pan, that sort of thing. So turn the wizard back on, and we can just jump straight ahead to choose outlet locations. and create outlet point. And I want to drop that outlet. I got to be kind of careful. I want to get away from the main branch. This is where they all came together. This is the south fork. I only want the east fork, so I'm going to put it right here. Drop that outlet, click next, and then delineate watershed. And it'll think for a minute. It's got a serious amount of math to do as it delineates the watershed. I should have saved again before I did this, because there's every possibility the program could crash with what I'm throwing at it right now. And you'll notice down at the bottom in red it's counting up 67%, 75%, and so on. Yours may be going a little bit slower than mine, or faster if you've got a quicker CPU than I have. But alright, so when it's done thinking about it, close this. I'm going to save, although it's already obvious I don't have all the data I need. In fact, the watershed continues to the north, south, and to the east. The only thing that I haven't done wrong is the watershed doesn't continue to the west. So I don't have all of the area that I need yet, and so I have to just dump all of this. So you click the new button, and we're just throwing it all away. But the one thing that is preserved that's kind of nice is the view of the project area. And so I need to zoom out further than I did before, and I'm just going to save this, overwriting the previous version of it, and click next. Alright, so project boundary. This is where it's iterative. So I needed more watershed to the north, to the south, and to the east, and so I'm going to zoom out a level, and then remember here there was nothing to the west of it, so there's no sense including any of this area to the west, and so I'm just going to kind of drag the watershed this way. Okay, maybe there's a possibility I might have it now. I'm going to pan up a little bit more. I've done this enough times where I kind of know where the watershed is, but man, it's just going to be right at the edge of whether or not we get it with this one. Alright, so click OK, and then next, use web services. And I think what we'll see when we just only have the elevation data enabled, remember in the last time we downloaded 30-meter spatial resolution, meaning that each pixel has a width and a height of 30 meters. And so it assigns the same elevation to everything inside that 30-meter box. That's a pretty coarse resolution if you think about it, but it's not so coarse when you're looking at a watershed that's approximately 50,000 acres. So click download data from web. Now this time, because I zoomed out, I doubled the area that's being viewed. It's now suggesting a resolution of 60 meters. Because it knows that, I mean, I could choose 30 meters still. It would just take longer to download and longer to compute. And it's not necessary. It knows that if you've got such a big watershed that the spatial resolution of 60 meters will be fine. So click OK, and it went and got that 60 meter DEM data. So I'm going to close this. And I'm going to turn off the elevation mapping. Now you can kind of see just from the elevations, oh, I know where the stream is going to be, and I think there's a pretty good chance I'm going to have the whole thing. So we can see the east branch of it. Here's the south branch of the Mud River. So let's start the wizard back up. We need to do topaz because you notice there's none of those blue flow accumulation cells. So let's save this again. All right. Next. Okay, topaz. I guess I could have just skipped straight ahead by clicking over here in the sub-menu on the left. So click topaz. And normal program termination. It calculated it, so I'm going to close this, and I can see now those blue flow accumulation cells. Do I have a question? I hear someone's mic active.
Dr. White, I have a question.
Yes.
So here where it says the minimum flow accumulation threshold,
Yeah.
Yesterday I was having trouble. I think maybe it was because my watershed was too small to keep it at the normal like 25, and my
Yeah.
topaz lines weren't showing up. So I didn't
Yeah.
know if that, like, really what that means.
Yeah. So if you have a watershed that is only 20 acres, but you had this set to 25, you wouldn't see any flow accumulation cell in your watershed. Because what that
Okay.
means is it's only going to start showing that blue line when there's at least 25 acres of upstream area. So you,
Okay.
and you can feel free to change that around. I mean, uh, experiment to your heart's content on this. Like if I click on 5 and then apply, it'll automatically, you can see how now the density of those flow accumulation cells just kind of increased proportionally. Or I could say I only want to see if there's 100 acres of upstream area. Click apply. So you're absolutely right that it may, if you were having problems, it may have been that your watershed was smaller than what you had set as the threshold.
Okay. And I noticed my line sometimes, depending on what I'd set it as, sometimes it wouldn't include the entirety of the river.
Mm-hmm.
So do we need to make sure that it includes like all the branches, of the river that we're interested in, or does it matter if it only shows like the downstream part of it? I guess if that makes sense.
So I think there's two different things. There's where you put the outlet, and so where you put the outlet is going to determine like the watershed area that's included in the model. But the flow accumulation cell, where that forms, mostly depends on like what we've just been doing, like how much of the project area overlaps with what you actually want to be modeling. So
Okay.
I think maybe to give you more specific advice, we'd have to set up a Zoom, and I'd need to actually look at what you were working
Okay.
on, because it could be either of those two issues.
All right. That's all I needed. Thank you.
All right. Good. See, that worked great, everyone. If you have a question, feel free to chime in with the microphone. It's just like real life, using your mouth to ask the question. It's faster than typing all that. All right. So we have our branch. I'm guessing we might have the whole thing, but we need to look for our. You see that distinctive shape there on the screen? The road is going to follow that creek, and so we want to delineate just the east branch. And so I'm going to create the outlet. So go down here to choose outlet location, and I'm going to create the outlet point and drop it a couple of pixels to the east of where the east branch comes into the other two branches. So I'm going to put it right there. Oh, I hope I got it on the flow accumulation cell. I bet I did. All right. So once we've dropped that, we can go next and delineate watershed. And it'll think for a minute. I should have saved it before I did that. The program could crash. Jeffrey's already delineated. He thinks we didn't get it all. Let's see if that's true. It's thinking about it. 75, 85. All right, let's close this. Ooh, it's so close. Look at that. I mean, if there isn't any, if we're missing any, it's going to be just a couple of acres. I'm going to save this one because I like it. So click Save. Boy, we just barely. I wish you could zoom out at like it makes you double how much you see with each zoom out. I wish you could only like maybe zoom out by a factor of 1.5 or 1.2 or something, because I don't want to go get double the data that I've got right now, because that's awfully close. But Jeffrey says we need to zoom out, so let's zoom out. So throw it away. Do I want to save project? Yeah, I want to save it. All right, so let's see. Oh, by the way, before we toss this, it's saying 49,166, so about 50,000 acres. All right, so toss it out. Let's start the wizard again. I'm going to rename this one class demo file 2. Save. All right, save. Boundary. Okay. All right, so here is our distinctive roadway pointer and I'm zooming out some more. Alright, so now I'm all the way into Charleston. This is an enormous map. I've got Milton, Hurricane, Taze Valley, St. Albans, South Charleston, Charleston. So it's huge. When I click OK and go and get the DEM, it's going to say, well, how about 120 meters this time because I've zoomed out so far. So think of it. Each pixel in this elevation map has the area larger than a football field. So we're representing an entire football field of area with just a single elevation. So this is going to be a pretty coarse map, and there will be consequences from that. So we've got the elevation map. Click Next, Compute Topaz. It calculates and finishes, so close. Let's take a look and see what we've got. Turning off the elevation map so I can see. Here's my junction, but that looks pretty coarse, right? You're starting to see what I mean by like the fine resolution of an elevation map versus how coarse it is. Like that roadway shape that used to be kind of sideways U, now it looks junky. This junky low resolution map. It's like a digital camera from the early 2000s. Alright, let's delineate it anyways. We got to be careful though, because here is the east branch. We can see the south branch coming in. We don't want to click on the wrong spot, and we may get just like a little side, like two watersheds for dropping a single outlet. That sometimes happens. So click Choose Outlet Location, Create Outlet Point, and drop it. You can see where I put it there. Alright, next, delineate watershed. Alright, it's thinking about it. Down at the bottom, I'm getting a progress indicator. So did we have before, like 49,000 square acres. Now we've got, let me move that symbol out of the way so I can see the label. Can't get it. Let me turn this off. Maybe now I'll be... Oh, there it is. Okay. 50,880 acres. So we mostly had it before, but now we definitely have it. Alright, so we could do this all day, and maybe we should, but we're not going to. You've got a watershed on the screen there. What we want to do now is apply the NSS model to it. So does everybody have a watershed of some sort delineated? I mean, if yours looks a little different from mine, that's okay, because really the point is we went through this process of zooming out and panning and just making sure that we had the entirety of this watershed, and so we know its area, and we could trim the DEM. You know how to do that, right? That's the process by which we right click on the elevation data, trim with a polygon. We're going to trim it interactively, so click OK, and then you just draw a circle around your watershed. Double click at the end, and then it creates over on the left hand side a new one. So that's the old one, and the active one is this one. Oh wait, okay, the new one is the one trimmed, of course. So I can right click and delete the old one, and now when I save it, it would be slightly smaller because I only have the elevation data that I care about. The elevation data doesn't have to be on or off to do what we're doing next. What we're going to do next is move over to the hydrologic modeling module, and in the drop down box you can see the list of model possibilities. In class last time we did the rational method. We'll get a little more sophisticated this time with the NSS. So click on NSS. National Streamflow Statistics, remember, is that resource that's made available by the USGS, where they've published these analyses for all the different states, where they're looking at what factors contribute to peak runoff. And in West Virginia, they've done the regression based on the watershed area. So in the drop-down box you did NSS, and then we have here NSS in the menu across the top. So if you double-click on the model, it'll bring up the National Streamflow Statistics dialog box. That's one way to do it. Or you can go NSS, run simulation, and it brings it up. And the default is Alabama because it's alphabetical. So we'll scroll down and find West Virginia in the list. Oops, that has what I was looking at before. So if you can't quite see all of the text to begin with, you can make the window a little bit wider by just simply dragging on the side of the box, and now we can see the full name of the available equations. And across the top it's got, going back through time, USGS has previous versions of the publication that does this statistical regression. And so they've got the 87 publication, the 2008 publication. Let's look at the 2010 publication, and we have to know what region our project is in. And West Virginia is broken up into 3 regions. There's the Eastern Panhandle in the east. There is the Central Mountains, and we are in the Western Plateau. So we're going to choose the 2010 Peak Flow Western Plateau region and click select, and it puts that into the selected equations, and we can see the equation. Remember, I think we glanced at that before and saw that it was some function of the drainage area, and WMS has done the math for us. It's converted that 50,000 acres into square miles. So we've got a watershed area of about 80 square miles. So this is a pretty big. Brandy, did you choose to West Virginia, or are you on Alabama still? If you switch to West Virginia, hopefully you'll be able to see. All right, good. So scroll down, and we want the Peak Flow Western Plateau. And then just click Compute Results. All right. So now what it's done is, Jeffrey asks, how do you access the NSS method screen? In the hydrologic modeling module, so click that, and then in the list of available models, choose the NSS drop-down box, and then click on Select Basin and double-click on the symbol for your basin. So that's one way to do it. The other is here in the menu across the top, NSS Run Simulation. So the default's in Alabama, but we need to drop down to West Virginia, Peak Flow Western Plateau 2010, click Compute Results. Alright, so like if we were interested in what's the 25-year flow, it says that the 25-year flow is going to be 7937 CFS. We can export this. So if you click on the export button, it's going to generate a CSV file, a comma delimited spreadsheet file that can be opened up with Microsoft Excel. So it gives us a default file name, nffexport.csv. That's descriptive enough, I guess, and it's going to be putting it into the same file that I've been saving everything else. So I'm going to click Save, and then let's go into Microsoft Excel and glance at what it's just generated for us. This is the output of the National Streamflow Statistics. So here in my browser, I can see, well, that was Milton 3. So I've got a lot of different files that it's created along the way. There's the WMS file that includes the elevation model. I've got that elevation map that I constantly am turning off. That's this. And then some previous versions. So NFF export, if you double click that, hopefully you have CSV associated with Microsoft Excel. and we zoom in a little bit here, looks like it's got some text I want to reveal. All right. So I can see the 2-year storm, the 5-year storm, 10-year storm, 25-year storm. So the peak flow during a 25-year storm, it predicts, is going to be 7937 CFS with a 30% standard error. So that means that the size of the 25-year storm could be plus or minus 30% from what's described there. So it could be as high as, well, what's 8,000 plus 30%? Maybe more than 10,000. Now why the big error? Remember that this national streamflow statistics, what we put into it was just the area of the watershed. So it doesn't know anything specific about our watershed's soil characteristics, land use characteristics. So there's just a lot of data that isn't accounted for there. But it's good to have those order of magnitude estimates, ballpark, 8,000 CFS. So you could do an analysis and find out, if there's a bridge in the area of that, what flow is going to be going under that bridge. Probably you wouldn't see a culvert for something this big. It's, we're out of culvert territory. The other thing I wanted to show you is that we can have it compute the hydrograph, and so it can show us visually what the hydrograph looks like. And so if I just highlight the row with the 25-year storm and then click compute hydrograph, it's going to want to know if we're taking that peak and we're defining the temporal distribution. You're saying what's the time to peak, how long is the rising limb and the falling limb, like what are its time-based characteristics. It needs to know the lag time of the basin, and so when we click compute lag time, it will bring up this list of possible equations for both lag time and time of concentration, and the one that I often go back to is the SCS method. And you may recognize some of these options that are available, the Kirpich, Kirby method. SCS method is a good balance because it's automatically calculated the longest flow path in the watershed. We have the average watershed slope, and this is an unusually flat watershed. South of Taze Valley, Hurricane, I guess things just aren't quite as steep there. That's why there's so much suburban development. But what we do need to have in here is the curve number, and a typical curve number for this area would be 70, and it's just going to be using that to calculate not the runoff amount, it's just using it to calculate the time of concentration / lag time. So you click OK, and now we have an estimate of the lag time, and it's going to use that estimate of the lag time. Now that it's done, I can click, if I just drag it out of the side, off to the side, maybe I have to close it. So done, and then double click the hydrograph, and you can see this is its guess of, we're going to have a peak of 8,000 CFS and when it occurs. So you can see that it's estimating that the 25-year storm, so a 24-hour storm, the most intense part of the rainfall, this is showing us for a pretty big watershed, not as distinct a peak as we often see. It's a pretty broad shape, but this hydrograph, the nice thing about it is that we could export this hydrograph. James, did you have a question?
Yeah, how did you pull up the hydrograph?
Double click on it. So just use your cursor and, you guys don't see my cursor, of course. Yeah, just double click on the hydrograph. Did that bring it up for you?
It did not.
All right. Are you in the hydrologic modeling module?
Yes.
All right. Maybe try the Select Hydrograph tool. By default, it generally would bring that tool up just because you'd created the hydrograph, but select hydrograph and then double click on the hydrograph. Did it bring it up now?
No, just bringing up the statistics method. The table was before.
What about across the top, the menu, hydrographs open? Oh no, that's not going to work. Boy, I don't know. Okay, so if it's bringing up the method itself, then what you're clicking on is the basin. So you need to go a little bit higher than that to get the hydrograph. So yeah, if I click on the brown rectangle, it brings up the method. But then if I'm a little bit higher and a little bit further to the right, it brings up the hydrograph. Not getting it?
No, I don't see it at all.
Well, it's possible. I mean, do you see the little icon on the screen? Like the small
No.
version of it?
Just the brown box.
So then that means you don't have a hydrograph. That's why you're not able to open it. So go back into the method itself, and all right, so highlight where it says rural, the 25 year, highlight that and then click compute hydrograph, this button down.
Okay.
And enter the lag time, click OK. All right, and then done. Now do you see the little icon for the hydrograph?
No, I don't.
All right, we'll have to, maybe we can get together on Zoom after class and maybe we can figure it out together.
All right.
Okay. So once you do have a hydrograph, you can export it. It's possible to get that exported to a text file, and you can right click and plot data. No, wait, export/print. So selecting export/print, and you could export an image of it if you were just going to be creating a report, but I think what's more useful is to export the text/data to a file, and then we would browse to a location that we want to save it. I'm going to have this be called hydrograph export.txt, and then click export, and the default option is we have to change it to data and labels and then table instead of list, and then it needs to know, like, do you want each individual data point in different columns or in different rows. And so the points/subsets is what we want to export. So we take it from list to table and from subset/points to point/subset. And then when you click export, what it's just done is it's created this hydrograph export.txt file, and you can open it up with Notepad, or you can open it up with Excel. So I'm going to click open, browse, and then I have to, by default it's just looking for Excel files, and so I want to open all files so that I can import the James got his hydrograph. Well done, James. You found the way. All right. So open that, and then it's going to take you through this import wizard, and we need to do next, and we're going to choose comma delimiting. And so it's looking for the commas in there, and it knows to put each set of numbers into its own column once it finds the commas. So next, finish. Alright, so we had two hydrographs on the screen since I exported the hydrograph twice. They're identical. But what you can see is if we go back to this hydrograph, we had about 700 minutes and peaking out at around 8,000 CFS. So the first column is time in minutes, and then the second column is CFS. And so it said about 8,000 CFS occurs at 279 minutes. All right, we're at 9:46. Just in the next couple of moments, we're going to get a first taste of the TR-55 method. So in the drop-down box, we're still in the hydrologic modeling module. Switch from NSS to TR-55. And so select TR-55, and then in the TR-55 menu, click Run Simulation, or you can just double-click on the basin, and now we have the TR-55 model up on screen. And a lot of the information that we know about the watershed has automatically been pasted in here, like for example the drainage area. Let's just double check that the time of concentration is satisfactory. So yeah, it looks like it copied over the time of concentration data that we had done previously when we were creating the hydrograph for the NSS method. So we still have our 4.91 hours for the lag time, and it's converted that into a time of concentration. Alright, so it wants to know what 24-hour duration rainfall depth do we want to have into our watershed. So before we were working with the 25-year storm. So in the precipitation data frequency server, which you are familiar with, of course, precipitation data frequency server, we can drag the target to our watershed area and then go down here into the table, and for a precipitation depth, 25-year 24-hour storm, okay, 4.23 inches of rainfall. Let's compare. So let's put in 4.23 inches of rainfall, and it's 70 curve number, type 2 distribution, rainfall distribution, and then look, the peak discharge that is calculated was 79.28. It doesn't line up that well in every case, but this is a particular situation where the National Streamflow statistics said our 25-year storm is about 7,900 CFS, and the TR-55 model is saying it's about 7,900 CFS. So, I mean, most probably we're in a pretty good, we're in the ballpark for sure that you're going to see about 7,900 CFS. Now, that's sensitive to the curve number, so if later on we're going to learn how to calculate curve numbers automatically using GIS data, what if the curve number was actually 65? Well, you'll notice that down here the peak discharge automatically is updating based on the change to the curve number. So this is using this TR-55. It uses the NRCS method for the rainfall runoff relationship. Remember, the rainfall runoff relationship is based on the land use and soil type characteristics that goes into curve number, how much of a rainfall hydrograph turns into rainfall excess. And so we are using the using NRCS method for rainfall runoff, and then we're getting a unit hydrograph out of that. You know, the time of concentration, we use the SCS method to find out what the peak is going to be. So you could get an idea of the sensitivity of the model to curve number by changing that curve number. But I've done quite a lot of watershed modeling in that area, and a curve number of 70 would be typical. All right, we are out of time for today. Boy, isn't WMS great? It's a lot of fun. I hope you find it as much fun as I do. Last look at these announcements here. So the exam will come into your email box at 8 o'clock on Wednesday. It'll also be on Blackboard. If you don't find it in your email, look for it on Blackboard, and then you upload your supporting documentation by 11 o'clock on Wednesday. So unless there are any questions about that or the activity we just worked through, I'll see you for another lecture on Friday, although you'll hear from me on Wednesday for the test. So feel free to send me an email if you have any questions, and of course I'm available by Zoom. If you had any problems in today's demo that you wanted me to take a look at, then just let me know. Thanks, have a good day.